Hello Physics 1 students and welcome to the Prelab 4 video. Today we're going to be discussing projectile motion. So as you can see, trigonometry is going to be vital to calculating different aspects of projectile motion. And this week we're going to be focusing on specifically sine and cosine. So sine is going to allow us to calculate the y component of the initial velocity, and cosine is going to allow us to calculate the x component of the initial velocity. So you may be wondering why you need to use trigonometry at all. Aren't they just going to give the components to you already in the word problem? And the answer is most of the time, no, they're not going to give you the components. And so you need to be able to use trigonometry in order to calculate your x and y components. The way that these problems are typically worded is they'll tell you that you have a projectile that's launched at a speed of, I don't know, 5 meters per second. So that would be this guy here. This is your initial velocity. So 5 meters per second at an angle of 45 degrees. So that would be this angle theta here. And it's going to be your job to break down this initial velocity into its y and x components. In order to do that, you need to know that the VOY is synonymous with the opposite side of a right triangle that's produced where the hypotenuse is VO, okay? And then VOX is your adjacent side, okay? And in order to solve for this equation, so you can see with sine, it's opposite over hypotenuse, right? And we already said that VOY is synonymous with the opposite side. And we already have established also that VO is the hypotenuse. So this literally means the same thing as this does. It's just different terms being substituted in. Same thing can be said for here. VOX is synonymous with adjacent, and VO once again is synonymous with the hypotenuse, so this also means the same thing as this. In order to solve for VOX or VOY, we need to multiply both sides by VO. Once we do that, we have VO cosine of theta on the left side of the equal sign, and then on the right side, we're left with VOX, which is what we're going to want to solve for. Same thing is true here. If we multiply both sides by VO, we have VO sine of theta is equal to VOY, and that allows us to solve for VOY. So I realize that there is a lot of text on this slide, and I'm not going to go through everything in a lot of detail, but I did want to mention that there are some really common projectile motion equations. And so some that you're probably going to have to use in most of the calculations that you're doing are position in the x-plane, and typically this is going to be x of t is equal to VOX times t. Typically you're not going to have a starting x position and you're not going to have an x acceleration, so a horizontal acceleration. Another really common one is your position in the y-plane, and I wrote it in two different ways. So I wrote it where I substituted g in for gravity, and then I also substituted in the actual value for gravity, but the idea is the same. So 1/2 gt squared plus voyt plus h, okay? A lot of times you are going to have all three of these terms, but of course, if you're told that you start at rest, then of course you can get rid of this, but that wouldn't really be projectile motion then, would it? Or if you're told that you have no starting height, so if you're firing your projectile from the ground, which is very possible, and there will be a lot of problems that you have to do with a scenario like that, then this would be 0, right? So position in the y-plane, very, very common. A lot of times you're going to have all three variables, but there might be some times where you get lucky and, you just have the height and your t-squared term. Last but not least, the velocity in the y-plane. This is really important, as you've seen before, when you're trying to solve for the zenith of your motion, so the top point of your motion. So you'll be able to set this equal to 0 and solve for the time that you're at the top of your motion. So again, this is another really common one. So once again, this slide has a lot of text and I'm not going to go through everything in a lot of detail, but this is great if you're one of those people that needs to memorize how things are done. I have listed below how you solve for a lot of common things that you have to solve for with projectile motion. I'm hoping that this appeals more to my memorization people and my words people, because I know that typically you'll have people who are more math oriented, so if you show them the math, they understand it better, but then there are some people that understand the words better, so this is more geared towards helping those people. This is just a quick reminder before we dive into the pre-lab practice problems. So remember, when you're doing these kinematic calculations, keep them as simple as possible. So if you can avoid working with negative numbers, avoid working with negative numbers. And if they don't give you an initial position, set it to 0. The other thing is, please draw pictures. They help so much. Okay, it helps you keep your stuff organized. So any of the relevant variables, make sure that they're in your picture. Include whether they're positive or negative, which means you also need to include your origin. And like I said, if you do that, it's really going to help you keep your work organized. All right, so if you haven't already attempted the pre-lab practice problems, I'm going to recommend that you pause the video now and work on the 9 pre-lab practice problems. Otherwise, if you've already attempted them, let's go ahead and get started. All right, so pre-lab practice problem number 1. So there's a prompt that pertains to the first 3 pre-lab practice problems, and that is a ball is fired horizontally from a launcher that is 2.42 meters above the floor. The experimental range of the shot was measured to be 1.68 meters. What was the total time of the flight? So we're going to be looking for T final here, which if we come over and look at our diagram, that's this guy right here. But before we do that, let's go into detail about our diagram, all the variables that we want to have labeled here. Okay, so first things first, I labeled my origin, so that's here at 0, 0. Upward from there is going to be positive, downward from there is going to be negative, and then to the right is also going to be positive. And the horizontal axis is doing double duty here. As you can see, it is representing the X position, so the horizontal position, as well as the time. The vertical axis is just the Y position. Okay, so our initial position in the Y direction, as stated up here, is 2.42 meters above the ground. The initial X position, since it wasn't given to us, we're going to just say that that's 0 meters. The velocity in the X direction, we're going to be solving for that later. We don't know what that is, but we also don't need it to solve for the final time. But I just wanted to mention it and make sure that it was included in my drawing. The velocity in the Y direction, we know that this is equal to 0. How do we know that? Well, it was fired horizontally, right? So that means there's no vertical component, so it has to be equal to 0. Then acceleration, so acceleration in the Y direction, this is going to be negative 9.8 meters per second squared. It's negative because we defined down as negative, right? And of course, gravity is always downwards. Then in the X direction, we have no acceleration. How do I know that? Well, the problem didn't tell me there was an acceleration in the X direction. It would have to tell me, okay? If you don't see that there's an acceleration in the X direction, then there isn't one. It's 0, okay? And then last but not least, they told us what their experimental range was, so X final is equal to 1.68 meters. Now that's about it for the drawing. So let's get started on the problem. So if we write down what our position equation is in the Y direction, that's going to be negative 4.9 t squared plus 2.42. Okay, as I mentioned before, the velocity in the Y direction is 0, so that's why we don't have that middle t term. All right. Next thing that we're going to do is we're going to set y of t equal to 0. Why are we setting it equal to y is equal to 0? Well, because we want to know t final, right? And that's when the object is on the ground, right? It travels some distance until it hits the ground. which is y is equal to 0, as you can see here. So that's why we're setting the position equal to 0, and then we're solving for t. That way we can figure out what the time is when the object is on the ground. Okay? So we're going to take our negative 4.9 t final squared, move it to the other side of the equal sign. Then we're going to divide both sides by 4.9 because we want to get the t final squared by itself. All right, so we take the square root of both sides now so that we can just get t final, and we get the t final is plus or minus 0.7 seconds. Now, how do we decide which one is right? Is it plus or is it minus? So there are two ways that you can do this, right? You can look at your drawing and you can say, okay, how did I define my origin? Okay, this is 0, 0 here. To the right of it is positive. Well, that means that my positive root has to be the right one. The other way that you can do it is you can look at what your t initial is, and you can see that it's 0, right? And so having a negative one would mean that it happened before the motion took place, which that doesn't make any sense at all. So it has to be the positive one, okay? So you can see my logic down here, basically just summarizing what I just said. So we know that t final is in fact the positive root. All right, pre-lab practice problem number 2. So as I mentioned before, this is going to have the same prompt up here, but this time we want to know what was the initial speed of the ball. Okay, so as we mentioned on the previous slide, this is a horizontal projectile. This means that there is no initial vertical velocity. This guy right here, we've established that. So we are looking for VOX, all right? That's this guy here, that's this guy here. Okay, and in this instance, VOX is equal to VO, right? Because we don't have a vertical component to our velocity. Now, I'm not going to go through all the details of this drawing because we already did that on the previous slide. Hopefully you were paying attention. So let's just jump right in. So we know that T final is equal to positive 0.70 seconds. Then we know that the range is equal to x final, right? That's how I abbreviate it in terms of variables. X final is the range. And this is equal to VOX times T final, right? So that big long position equation, we don't have an initial x position, right? Or it's 0, and we don't have an acceleration. That's also 0. So all we have is that middle t term, VOX times t, okay? Now, we're going to plug in our values. So we know that the range is 1.68 meters. We don't know what VOX is, that's what we're solving for, but we do know what T final is, right? We solved it in problem 1, and that's 0.7. So now we're left with 1.68 is equal to 0.7 VOX. So in order to get VOX by itself and solve for it, we need to divide both sides by 0.7. And we get that VOX is equal to 2.40 meters per second. And that is the final answer. All right, pre-lab practice problem number 3. So once again, we're still using the same prompt up here, but this time we have a new question. So if the theoretical range for the same shot was predicted to be 2.72 meters, calculate the percent error. Use the theoretical range as the reference value. Okay? So this is the information that hopefully we know. So theoretical, they told us was 2.72 meters. Experimental, we know is 1.68, right? That's in the prompt up here. And we're going to calculate percent error. The equation for percent error is the absolute value of the theoretical value minus the experimental value divided by the theoretical value times 100. Okay, so it's a simple plug and chug problem. Theoretical is 2.72, experimental is 1.68, theoretical is 2.72. Multiply by 100, and you get that there is a 38% error. All right, pre-lab practice problems numbers 4 and 5. So now we have a new prompt all the way through problem number 9, and that is a ball is fired from a launcher with an initial speed of 7 meters per second at an angle of 30 degrees from the horizontal. The point of firing is 2.42 meters above the floor. Now I realize that we are doing two at the same time, but they kind of go hand in hand. This is the trigonometry where we're breaking the initial velocity down into its components. Okay, so In the x direction, so that's number 4, we have ka, right? That's the second part of SOHCAHTOA. So we have cosine is equal to our adjacent side over our hypotenuse, right? We already talked about this when we were going through the lecture portion. That means that cosine of theta is equal to VOX over VO, or simply if we're trying to solve for VOX, we can rearrange this, right, to be this equation down here. So we have VO cosine of theta because we just multiply both sides by VO, right? The other part is the SO part, so the sine part. We know that sine of theta is equal to the opposite over the hypotenuse, and we established that the opposite side is VOY and the hypotenuse is VO. So in order to solve for VOY, we multiply both sides by VO, right? So then we're left with this equation here. So VOY is equal to VO sine of theta. So the two values that we're trying to find, so number 4 is VOX and number 5 is VOY. So since number 4 comes before number 5, let's do number 4 first. So VOX is equal to 7 cosine of 30, right? Because VO is 7, cosine of 30, theta is 30 degrees. Okay, so we find that VOX is equal to 6.06 meters per second. Then we come over here to VOY, and we have VOY is equal to 7 sine of 30 degrees. So we multiply that out, and we get that VOY is equal to 3.5 meters per second. And that is our final answer. All right, pre-lab practice problem number 6. So as I mentioned before, this prompt is going to stay the same all the way through problem number 9. But this time for problem number 6, we want to know what is the total time of flight. So we're going to be looking for T final, which is this guy down here. Okay? But before we do that, I just want to make sure that everybody understands where everything came from on our drawing. So let's go through everything. So the prompt told us that we are starting 2.42 meters above the ground, so that means y naught is equal to 2.42 meters. The starting x position is 0 meters because they didn't give us one, so why muddy the waters and make it more complicated? Just set that equal to 0. Then the initial velocity. In the prompt, they told us that the initial speed was at 7 meters per second at an angle of 30 degrees. In problems 4 and 5, we broke this down into its components. So the x component we found to be a positive 6.06 meters per second, and the y component we found to be a positive 3.5 meters per second. Now, how do I know these are positive? I'm glad you asked. So if you look at our origin down here, we're at 0, 0, and upward from there is positive, and downward from there is negative. So since this arrow is pointing upward, we know that that's positive. Since this is pointing rightward, we know that is also positive. Okay? Now, for the acceleration, in the y direction, we have gravity, and that is, of course, in the downward direction. So since we define down as negative, we want to make sure that we carry that negative sign. So negative 9.8 meters per second squared. Then our acceleration in the x direction is 0 meters per second squared. Now, if you're wondering, how do I know this? The way that I know this is because nowhere in the problem or this prompt here do they tell me that I have an acceleration in the horizontal. Therefore, I can assume that I do not. And then this isn't really relevant just yet, but up here you can see the time of our turnaround, and so the time would actually be down here on the x-axis, right? And the position, so the y position, y turn, would be this point up here, okay? Now once again, even though it is not labeled as such, I have the horizontal axis doing double duty. Okay, so this is both the x-axis and the time axis. And then the y-axis, once again, is just in the y direction. But keep in mind that this is from a graphing calculator, and so you can't exactly expect the x terms to precisely line up with where they should really be, but you will see that the time turns terms line up. So just keep that in the back of your mind. When we're talking about an X graph, I will provide the actual X graph, but for the most part, most of these questions are going to be concerned with Y positions and T's, so times, and so that's why I just have this graph here, where the grid in actuality represents the Y positions and the times. All right, well, without further ado, let's get started. So we're trying to find the final time, so the time that the object is at 0 meters, at a height of 0 meters, that's right here, okay? Because we want to know the total time of the flight, right? So that's when the projectile hits the ground. Okay, so in order to solve for this, we're going to set y of t equal to 0, right? We want to set our position equal to 0 because that's the position of the projectile when it lands. And we want to calculate the roots of our quadratic equation. And we're going to assume that t initial is equal to 0, right? And we have it labeled in our picture, so we're not so much assuming as knowing, defining that. And the t final root is going to be the positive one, okay? We're going to get a negative and a positive root. You can see that right here. It intersects at a negative number and it intersects at a positive number. We want this positive number, okay? So this is our quadratic equation, right? And we are going to need to use the quadratic equation to solve, right? So the negative b plus or minus the square root of b squared minus 4ac all over 2a. So we're going to be using that mess in order to solve for our time. Okay, so once we do that, we get one of our roots is equal to negative 3.5 plus 7.725 over negative 9.8. And this turns out, unfortunately, to be our negative root. So this is not the one that we want. This is bad. The one that we do want is this guy. So that's the negative 3.5 minus 7.725 divided by negative 9.8. So t final, that is the correct t final root. So t at 0 meters is equal to 1.145 seconds. And you can see in the illustration too that this does check out. So this is correct. This is our final answer. All right, pre-lab practice problem number 7. What is the predicted range of the shot? So as promised, when we do have an x variable as one of the relevant variables, that's actually what we're solving for. I have included the x plot so that you can see actually where that value would be if we were to graph the x of t equation. Remember, the range is the position on the x-axis when the object hits the ground. So as I mentioned, we are looking for the range, and the way that we're going to do that is we are going to plug t final into our x of t equation. So first things first, let's write down what the x of t equation is, okay? And then let's plug in our values. So we know that there's no acceleration, right? We've established that right here. We know that the starting position is 0. We established that here. So all we have is a velocity in the x direction, and we figured that out in problem number 4. So we know that x of t is equal to a positive 6.06 times t. Now we're going to get into the business of plugging in our t final into the x of t equation in order to solve for the range. So x final is equal to x of t final, and that's equal to 6.06 times t final. Now we know what t final is, so let's plug it in. We just solved for it in number 6. So t final was 1.145. So the range is simply going to be 6.06 times 1.145. And that gives us a range of 6.94 meters. And that is our final answer. Then you can see over here where we graphed our x of t equation, which is 6.06 times t. It's obviously it's a linear equation, right? And you can see up here at the time 1.145, we have the range 6.939, or rounded off 6.94. All right, pre-lab practice problem number 8. How much time did it take the ball to reach the top point of the trajectory? Hint: what is so special about the vertical component of the velocity at that point? Okay, so for pre-lab practice problem number 8, we're going to be finding t-turn. Okay, so that's this guy up here, or this point on the graph. And the hint here is asking what's so special about the vertical component of the velocity. Well, that's that it's equal to 0, right? We know at the top point of the motion, the velocity in the y direction is equal to 0. All right, well, nothing's really changed in the drawing, so there's no sense dilly-dallying. Let's just get right to it. So we're going to be setting the Vy of t equation equal to 0, and we're going to be solving for t, as we have done many times before. So Vy of t is equal to ay times t plus Voy. When we plug in our values, that gives us a negative 9.8t plus 3.5. We're going to set that equal to 0, as we mentioned up here, right? So we set it equal to 0. We move our negative 9.8t turn to this side, so that becomes positive, and then that's set equal to 3.5. Then in order to isolate our t turn by itself, we need to divide both sides by 9.8. So we divide both sides by 9.8, and we get that t turn is equal to 0.3571 seconds. And that is our final answer. Now, I realize that I didn't round that off, but you can round it off on your own. All right, the one we've all been waiting for, the last pre-lab practice problem. Problem number 9. So we want to know what is the maximum height of the trajectory. Okay, so this time we're going to be finding y turn. That's this guy up here. So this spot on the parabola up at the tip. Okay, and the way that we're going to do that is we are going to plug t turn into y of t. Okay, so just a refresher, this is our position equation. We're going to plug in our known values, right? So negative 4.9t squared plus 3.5t plus 2.42. Then we know that y turn is equal to y of t turn, so that's equal to negative 4.9 t turn squared plus 3.5 times t turn plus 2.42. Now let's plug in that t turn value that we got from problem 8. So we plug in 0.357 everywhere we see t turn, so we have negative 4.9 times 0.357 squared plus 3.5 times 0.357 plus 2.42. Now, when we multiply everything out and add it up, we get that y turn is equal to 3.45 meters. And this is the correct answer because if we check over here on our graph, we can see that it appears in the correct spot. And so we know that it has to be right. And not just because I reported the value, right? You can see that up here we have 3 and it's just slightly above 3, right? So this totally makes sense. So I realize that this isn't one of the pre-lab practice problems. This is just a bonus question to kind of review and practice a little bit more. But if you would like to know how long it would take for the object to return to its starting height, so 2.42 meters, then stay tuned because I'm going to go over that. So like before, we're going to be using our position equation y of t, and just to reiterate, that was negative 4.9t squared plus 3.5t plus 2.42. Now in this instance, we're going to be setting y of t equal to 2.42, and we're going to solve for t. The reason that we're setting it equal to 2.42 is because we want to know when it returns to that starting height. Okay, now if they wanted to know a specific height, so say they wanted to know when does it get to 2 meters, of course you're going to have a couple solutions for that. And of course you can see here, one of them is going to be negative and not valid, and then another one will be valid. So you could plug in any value there. So any problem that's asking you how long it's going to take to get to a specific height, you can set your y of t equation equal to that number. But of course, in this case, I just want to know the returning height, the starting height. When does it get back there? So we set it equal to 2.42. Okay, and of course, this is equal to negative 4.9t squared plus 3.5t plus 2.42. Okay, we know that the 2.42s are going to cancel on both sides. and then we're going to be left with 0 on this side. Now we're really getting into solving for the time at 2.42 meters, right? So we're going to factor out a t from both of these terms. And so when we factor out a t from both terms, well, it's not surprising. We know that this t is equal to 0. And of course it is, right? We defined the t initial as 0. Our starting height is at 2.42, right? So this is a pair, a yx pair, right? Or an xy pair. It's not surprising that we have a 0. Now the other term is not going to be 0. So I trust that you can solve this simple algebraic formula, and when you do, you will find that the other t is equal to 0.71 seconds. Okay, so the time that it returns to that starting height is going to be 0.71 seconds. And if we check it on the graph over here, we can see that this vertical line here, this is at 0.7, and it's just to the right of that, so 0.71, that checks out as far as double checking with the graph. So we can be pretty confident that we're right. So that's pretty much it on projectile motion. If you'd like to stay tuned, I'm going to review kinematics and free fall, because, spoiler alert, there actually is going to be some kinematics and free fall stuff on the quiz. So you can see here we have a ball that's thrown upward on the moon, and its position can be explained by the equation y of t is equal to negative 0.8 t squared plus 13t plus 2. And then over on the right hand side I have an illustration of that motion taking place. Now my question for you, well, questions for you are, what is the moon's gravity? So what is AY? What is the initial velocity, or VOY? What is the initial position, or the starting height of the thrower, or Y naught? And then using the position equation to solve Vy of t, what would your Vy of t equation be? So that's going to be really similar to what you did in Lab 2 in one of the tables when you solved for Vy of t. So now I'd recommend that you pause the recording and figure out the answers to the 4 questions, and then unpause it and check your work against my answers. All right, so here are the answers to the 4 questions. So AY, or the moon's gravity, is equal to negative 1.6 meters per second squared. The way that I got that is I multiplied the negative 0.8 by 2. Remember that the coefficient in front of the t squared term is 1/2 a, right? So to get a by itself, I need to multiply this by 2. That gives me negative 1.6 meters per second squared. Now VOY, VOY is just the coefficient in front of the t term, so that's simply 13 meters per second. Y naught, that is going to be our constant, which is 2. So the height of the thrower was 2 meters, about 6 feet. And then last but not least, the Vy of t equation would be negative 1.6 t plus 13. Remember that Vy of t is Ay times t plus Voyt. All right, so let's do a free fall review problem where we're trying to find y turn. So that's going to be the highest point of our motion. All right, so in order to solve for y turn, first we need to set Vy of t equal to 0. Okay, so when we do that, that allows us to solve for t, or t turn specifically in this case. So we set Vy of t equal to 0. So this is our Vy of t equation up here, and we've set it equal to 0. Now we take our negative 1.6 t, we move it to the other side of the equal sign, so now it becomes a positive 1.6 t, and it's equal to 13. In order to get t turn by itself, we need to divide both sides by 1.6, so 13 divided by 1.6 gives us t turn, and that is 8.125. Okay? So that means that it takes 8.125 seconds to reach its highest point. Then we take t turn and we plug it into our y of t equation. That's this guy up here, in order to find the corresponding position of the object in the y plane. Okay, that is y turn. So y turn is equal to y of t turn, so 8.125. And that's equal to negative 0.8 times 8.125 squared plus 13 times 8.125 plus 2. All right. When we multiply and add up, we get that this is equal to 54.813 meters. Yes, I realize that that is really high, but you have to remember that the moon's gravity is very, very small. All right, so now let's do another free fall review practice problem. This time, let's find T final. So what do I mean by T final? I mean the time that our object is going to hit the ground, okay? So what we're going to do is we're going to solve for T final by setting y of t equal to 0, right? Because that is what we've defined as the ground. Okay, so we set y of t equal to 0. Once again, this is our y of t equation up here. So 0 is equal to negative 0.8 t squared plus 13t plus 2. Now, unfortunately, this equation doesn't factor easily, and so we have to use the quadratic equation. That's this guy here. Okay, this is with all of our values plugged in, and then we find that the two roots of our equation are negative 0.152 or 16.402. Considering that we started at a time of 0, this negative root doesn't make any sense because it took place before the motion took place, and so our answer is 16.402. And the unit is seconds. And if we take a quick look at our graph over here, this is the point that we're talking about, and we can see that this would be 12, 14, 16. It's just a little bit past 16, so it checks out on our graph as well. All right, one more free fall review. So this time we're going to find the time that it takes to return to the 2-meter height. Okay, so this is where we start at 2 meters, and we want to know when it returns to that starting height of 2 meters. Okay, so what we need to do is we need to set y of t equal to 2. Okay, so we set y of t equal to 2. Remember, this is our y of t equation up here. So we know that these 2's are going to end up canceling, so then we're just left with negative 0.8 t squared plus 13t. So then we can factor out a t from both of these. So then we have t times a negative 0.8 t plus 13. Well, obviously this guy is 0, right? Because that's our starting point, t initial, right? And the other one, the one that we're looking for, so when it returns to the initial height, that's going to be solving for this root. Okay, and so when we do that, we end up finding that it is 16.25 seconds when the ball returns to a height of 2 meters. And if we want to check it on our graph, which of course we do if we have it, that's going to be this point right here. And we can see that this vertical line here represents 16, and it's just a hair past 16. And so once again, our answer checks out. All right, so I want to take a few minutes to go over some kinematic relationships since it's been a couple weeks and this is going to come up on the quiz this week. All right, so the first kinematic relationships I want to talk about are the kinematic relationships between a quadratic position equation in one dimension. So that means that it has constant acceleration. And in this example, I'm going to say that that constant acceleration is gravity, because of course that's probably the most common acceleration that you're going to be working with, and that's equal to negative 9.8 meters per second squared. Okay, so here we have our position equation. Y of t is equal to 1/2 gt squared plus VOY times t. Now you can see I opted to not have a starting height. That's why our parabola is starting here at 0. But what I really wanted to drive home here is what's going on with the velocity. Okay, so if we have a larger time frame and we take the slope of the position and the time, we get the average velocity. right? So the slope of this line, so if this is t initial and this is t final, the slope of this line is going to tell us what the average velocity is. And you can see here that this looks like a pretty flat, pretty horizontal line, right? So the story that this is telling us is that the average velocity is 0. And that makes a lot of sense. And I'm going to explain to you why that makes a lot of sense. So over here, you can see that this parabola is symmetrical, right, about this dotted line. Over here, if we were to find the instantaneous velocity, which we would do by drawing a tangent line, you can see that it would have a positive slope. And there are infinite number of possibilities here, right? We could draw tangent lines anywhere. But regardless, we're going to have bigger positive numbers down here that get smaller and smaller as we approach our highest point. Up at the highest point, we have a horizontal line, right? And this makes a lot of sense, right? Because we know that the velocity in the y direction is equal to 0 up at the top, right? So that's literally what this is saying. If we take the slope at the highest point here, then we get a slope of 0, which is exactly what we would expect. Then when we pass the turning point, you can see that we would get tangent lines. If we drew a tangent line over here, we would have tangent lines that have negative slopes, right? These are going to have small negative slopes, and these are going to have bigger and bigger negative slopes. So if you think about the average velocity being the sum of all of these slopes divided by however many of them there are, that's going to come out to about 0. So that makes a lot of sense. So basically, what I'm trying to say here is when you are taking the slope of the position graph, when you have a quadratic position equation, or even if you don't, regardless, when you're taking the slope of the position graph, you are getting velocity, okay? Now let's come over here and take a look at velocity. Okay, so our velocity graph. So velocity is equal to gt plus VOY. Now remember, gravity is negative 9.8. So that's why we have a negative sloping line, right? Because this is a negative slope. And then VOY, our y-intercept, right, is going to be right here. This is our y-intercept, and it just goes down from there, okay? So now, if we were to take the slope of our velocity graph, if we take the slope, you can see that it's a line, right? And so it's not changing, it's constant. And the slope of said line, as we can see right here, is gravity, right? And this makes a ton of sense, right? Because we said that it's a constant acceleration. And here we are proving that right here graphically. If we take the slope of this line, no matter where we take it, because the slope of a line is constant, we are going to get gravity. Or if you use something else, you're going to get your acceleration. Then if we come over here to our acceleration graph, it should come as no surprise at all that all we have is a horizontal line at g, right? That's it. No matter when you are, no matter what time you plug into the left side of the equation, you're always going to get g out. That's it. You have a constant acceleration, and that's exactly what this graph is illustrating. So hopefully you found in the previous slide helpful and a good review of things that you already knew. You've probably done a lot of practice problems where you had quadratic position equations, but what you might not have done a lot of is linear position equations. So I'm going to go over a linear position equation example now. Okay, so when you have a linear position equation, this means that you have a constant velocity. Okay, and arbitrarily, I decided that this constant velocity is going to be equal to -2 meters per second. Okay, so it's going backwards at a rate of 2 meters per second. All right, so if we take a look at our position versus time graph, it should come as no surprise that it is linear, right? Because that's literally what I said I was going to do. We're going to do a linear position equation, right? So we have a linear position equation. This is equal to VOY times t. This is our slope term, our mx, right? Plus our y-intercept is y naught. So you can see that guy right here. Here's our y-intercept. And then this would be -2 times t, right? So the slope of this downward sloping line is going to be -2. Now, if you recall from the previous slide, the relationship between the slope and the position versus time graph, if we take the slope of the position versus time graph, we are going to get velocity out. Okay, the same is true here. Anytime you take the slope of a position versus time graph, you are going to get velocity. Now, this velocity is a little bit different than the previous one, right? Because no matter when you are going to get exactly the same velocity, right? This is a line, and so that means that we have a constant slope. So no matter when you are, if you take the slope, you're going to get -2 meters per second, right? Now, if we move on to our velocity versus time graph, it should come as no surprise that we just have a horizontal line at VOY, right, at -2, okay? Because we know that no matter where we take the slope of this line, or no matter when we take the slope of this line, we get exactly the same velocity. That's because we have a constant velocity, okay? So you can see that illustrated right here. So now if you recall from the previous slide, when we took the slope of the velocity versus time graph, we got acceleration. And indeed, if we take the slope of this horizontal line here, which we know the slope of any horizontal line is 0, then that's our acceleration, right? And that makes a lot of sense because we know that acceleration is the change in velocity over the change in time. So if the velocity is not changing, then there can't possibly be an acceleration, right? So that totally checks out as well. Then if we move on to acceleration versus time, it should come as no surprise that our acceleration is always 0, no matter when we are. Our velocity is not changing, therefore we do not have an acceleration. All right, well that's about all that I've got. I hope that you found this review helpful, and best of luck on the quiz.